Welcome back to the series. In video 101, we touched on LangGraph basics. In 102, we extended the graph with tool nodes, conditional edges, etc. Now, I have to say, those two videos have been very well received by you guys. For that, I thank you. I also got a lot of suggestions and requests to make the series better. So here we go. I have added an extra video, 103A, which goes a bit beyond the basics. I've also augmented the next video, 103B, with a deep dive into tool callings, besides testing our graph with other models. Anyway, in this video, we'll cover data structures, state changes, conditional edges, routers, and reducers. That said, let's get started. Alright guys, so before we get started, I figured we touch upon these four pillars of LangGraph: the graph, state, nodes, and edges. So the graph, the complete workflow, the overall structure that combines nodes and edges into a cohesive executable process. Here we're talking about the state graph that holds the entire graph. Next, the state, the data shared across the workflow. It's the data structure that carries and tracks information as it moves through the workflow. Remember the typedict class, pydantic, etc. that gives our data the structure it needs? That's what it is. Next, nodes, steps that modifies the state. Nodes are the individual steps in the workflow, each performing a task or transformation on the state. Now these could be our agents, tools, chatbots, you name it. These are the guys who accomplishes the tasks, the worker bees. Next, edges, the connection between the nodes. Edges define the order or conditions under which the action threads occur in the workflow. Basically, the traffic cops that maintain the direction of the flow. This is where an agent can decide which tool to use, which other agent to hand over their output to, etc. Let's hit the code. Alright guys, so let's get started here. As far as installation goes, as you can see, we only need LangGraph here. And the current version I just installed is 0.2.64. This is supposed to be the latest and the greatest. With that being installed, let's take a deep dive into LangGraph. Alright, so to take the deep dive, we're going to go through these few sections. First, data structure, where we compare typedict versus pydantic, and then basic concepts on nodes, edges, and state. Then comes state changes, conditional edges, and router functions, and at last, reducer functions. So let's hit data structure first. All right, this is not LangGraph. Here, we're just going to compare two data structure libraries of Python, typedict versus pydantic. Just as a reminder, let's go back for a second. You probably remember this from our last video. This is where we actually created the state data structure by extending typedict, right? So that's what we're going to talk about. In here, let's say this is going to be our data structure for our next graph. Simple enough. One string and one number, right? So that's why we create a data structure class called person by extending typedict. And here we clearly mention name would be string, age would be integer, right? And then according to that, we create an object called person, which would have this data structure. So now, as you can see, we're putting name and a string fine, but age, we are putting in another string. We're completely avoiding putting an integer in there, right? So now if we run it, watch what happens. Boom, there you go. It prints out fine. It just does not give us any sort of warning or error message or nothing. What I'm trying to say is typedict offers a much more relaxed data structure. That's why we use this mostly during design time. For example, as you can see here, we are using the Google Colab, and this is what we normally use for prototyping and during the design time, right? And that's when we don't need, very strict data structure that will fail us. But when it comes to production, we're going to need something that will give us error message or that will give us type hints during runtime, right? Even though, this same program we can run using the static linters like MyPy, and that will actually show us the issue, but it's not going to happen by itself when we are using typedict. So for that reason, during production time, we have to use, or I should say we should use the pydantic. And in here, we're bringing in the base model, and we're creating the same new data structure called person. And this time we're extending base model instead of typedict. As we try to create this person object during runtime, watch what happens. Boom, there you go. It actually caught the error. See here, it's supposed to be integer, but we're using string here. And as soon as we do, when we try to run it, pydantic will stop us and tell us one validation error for person. It's going to be very clear about it. All right, so that being said, let's move to the next module. All right, so let's go over these basic concepts one more time. I'll show you some interesting outcomes using this graph. First off, let's bring in the typedict from the typing library, and then the end node, start node, and the state graph from LangGraph. And first of all, we're going to go ahead and create our input data structure by extending typedict. Just as a reminder, let's go back. Right here, you probably remember from our last video. So this is how, by extending typedict, we created our state data structure, right? Now let's go back. So in here, though, we have our two different variables declared: string var, which is a string, numeric var, which is int or integer, right? With that being done, we move to creating our main node function, which is change state, and that will take an input, this structure, and all it will do is just print out the current value of the input and then return the value, nothing else, keeping it very simple. And of course, then we bring in the state graph and pass input state as an argument to create our main graph structure. With that done, we go ahead and add two nodes, branch 1 and branch 2, and in both cases we use the same change state function. At one point I actually thought these functions gives us the structure of the graph, but turns out these names are the ones that actually gives the structure. You can use any function you need in here as many times as you want. That said, we go for our edges. Here we go ahead and add branch 1 as the start node, and then we connect branch 1 and 2 by adding a normal edge. And finally, we end the graph by denoting branch 2 as our end node. And this is just a different style I'm showing you here to declare a start and an end node. You probably remember we did it differently previously, but we'll get to that. So once this structure is done, we can just simply use graph.compile to create a runnable. And a runnable is something that you can actually invoke or stream in LangGraph or LangChain. Now let's run this and see what happens. All right, so this is now the structure of our graph. It's a very simple graph, but let's see what happens when we decide not to have a starting point. Boom, it crashes, and it clearly tells us graph must have an entry point, right? So let's give that, but this time we're going to remove the endpoint and see what happens. Boom, it ran fine. But what it did, it took the last branch, which is branch 2, took it as a de facto end node. But there's a caveat to it. This is a simple graph, but if this was a large, more complex graph, this could be a problem. Because as long as we are not officially declaring an endpoint, this part of the graph remains open. So this branch 2 then will attach itself to any next node it finds, thus causing very complex, unpredictable behavior. You might be seeing like, oh, my graph is running, but I'm getting weird results, and this would be the one. For that reason, you always need to officially close it down like this. Now let's see another way, which we are used to, more professional way. We're going to go ahead and declare our start and end node. Let me bring that code in. All right, so this is the way. Set entry point branch 1, set finish point branch 2. So this is another way, more professional way to declare the start and end point. So let me run that, and we get exact same thing, which is great. But now let me show you something. Let's assume this is a complex graph and somebody makes a mistake here. Watch what happens. Boom. The whole thing breaks and creates some weird results. I mean, this is fine here, but imagine once again, if this was a complex structure, that little mistake can throw you off by a mile. So we fix it like this, run that, and we get our structure back. And now that we have our structure back, let's try to invoke it with a single input value like this. As you remember, we have two values in our input state structure, right? But we're using type dict, so watch what happens. Boom. So what we see now is the current value print out the string value a. Basically what's happening is this change state, this print value, it ran twice because we used it twice. So we get the same value twice and one return, like we have here, just the return input. But it didn't crash or give us any kind of runtime error because of that type dict. And this is great for design stage or prototyping stage, right? Now let me show you another thing. So this time we're gonna give it the right structure, one string and one numeric value, and run it. And we get the expected result, two printouts and one return, right? Now watch, if we use a third set of values, right? Another list of numbers. So watch what happens. Look at that. Exact same result. And this is where type dict also kicked in. Even though it doesn't declare all sorts of runtime error, but it maintained its integrity right here. One value, as long as it matched its structure, it took it in, no problem. Second value, fine, as long as it matched, but you try to give it third value, it silently ignores it and gives you the accurate result anyway. So that's where the value of data structures comes in. And of course, once again, I would suggest you to consider Pydantic for this purpose whenever we are doing production-based work. With that, let's move to our next module. All right, so we start this new graph exactly like before, type dict, end and start node, and state graph, by bringing in type dict from typing, and end and start node and state graph from LangGraph. And we declare an input state with type dict. And this time also we have a string variable and a numeric variable. And this time we're calling our node method modify state, which will take an input as input state. What it's going to do, it's going to go ahead and add a to our string variable and add 1 to our numeric variable, which means if this is iterated, each time it goes ahead, it's going to keep appending an a to the string variable and adding 1 to our numeric variable. And next we declare our router function, which also takes the input state variable as an input. And we have a simple logic here, checking on the numeric variable. Up until this is 5, it's going to keep looping and returning branch A. Else, it's going to return end. Then we go ahead and create our graph with state graph and passing input state through. And then we go ahead and add two nodes, branch A and branch B, both using the same node function. Then we add branch A and B by adding an edge between them. Then comes our conditional edge, and that's where the fun begins. Here we are adding the conditional edge to our branch B. We're calling in our router function from here, and we are also giving it a data mapping. Now this is something new. As you can remember from our last video, here we had a simple conditional edge. We just returned the tool node or the end, and we added that to our prompt node just by adding our conditional edge. It's pretty much hard coded. But here, since we have a data mapping feature, so that means this router becomes a variable router or a symbolic router, which can be used over and over with anything else, because we have a data mapping here where we can map branch A to anything else, and that's where it's gonna go. We don't have to be tied to branch A here, right? Don't worry, just after we run this, I'm gonna go ahead and give you some good example that will help you understand what's going on. So now that we have our conditional edge, we set an entry point with the branch A. We no longer need an endpoint here because our conditional edge takes care of that. Once that's done, we go ahead and compile our graph and turn that into runnable. And let's see what our runnable looks like. Boom, it's start node, end node, and then in between our branch A and B talking to each other in a loop. That's the kind of relationship they have in between. So let's run this with a string variable A and numeric 1. And as you can see, as expected, 5 A's and numeric value 5. We got our result. Now here, I should augment it by saying, maybe you would understand it better if I just change this. Instead of branch A, say branch, making it into a variable, and then assign the branch to branch A or whatever, and then run it. Oh, there you go. See, now exact same thing, but now you have a nice little variable showing up. It's actually denoting that, hey, this is a variable. You can put any node and throw it in here, and it's gonna go ahead and finish it. Now let's go explain it a little bit better. The difference between the direct router versus the symbolic router. Now, the direct router would be from our previous video where we just returned a node or a stop node, and then we created the simple conditional edge by adding the previous node to our direct router. Simple as that. No variable, no nothing. But the new one, the symbolic router on the other hand, it has something like this. When the light turns green, return go, else halt. And then we take that and add a conditional edge to our previous node, use the symbolic router, but this time we tell our graph that go means the proceed node, halt means the stop node. So now our graph knows that this is just a variable, so whenever this hits this and goes ahead and goes to proceed node. Otherwise, goes to halt, which is the stop node. And that makes this router a symbolic router or a variable router, which can be used in many places over and over. With that, let's move to the next module. All right, so let's start another graph with type dict, and this time we bring in extra function called annotated, and the end and state graph from LangGraph, and from the operator module we're bringing in the add function. What is the add function? This is what it does. Simply adds two numbers. If 2 and 3 gets passed, it just outputs 5, or if there are two strings gets passed, then it just outputs a concatenated version. That's all it does. Let's go back. All right, so in here we declare a brand new input state structure extending type dict. This time we're going to have one variable that will have no value change, and it will be a string. Then string value annotated with string and add. Add here comes in as a reducer function, and annotated, what it does is it goes ahead and adds metadata to our given structure of data without changing the overall meaning. Simply means if we receive a string value here, it's gonna go ahead and add or concatenate to that string value as it keeps coming. Same way, if it's an integer, then it's gonna go ahead and keep adding to it, or if it's a list value, it's gonna just add another item to it. And why am I showing you this? Let's go back to our previous video. Remember this guy, add messages? We brought that in from graph messages, and that became the reducer function, and we annotated that as a list and added this add messages as metadata, which only meant that whenever our state receives a string, and it's going to go ahead and use this reducer function to add to this message as a list. just to demonstrate this fact, I brought in these guys. So now that we have our input state, let's move to our modify state function, which simply takes an input, returns it. Then we go ahead and create our state graph, pass the input state. Then we add two nodes, branch A, branch B, and in both cases we use modify state as our node functions. And then we connect A and B by adding a normal edge to it. And finally, we declare branch B to be the end node and then set branch A as the entry point. Finally, we compile the graph, turn it into a runnable, and we invoke that runnable with all these values. No change, A, string, A, numeric value, 1, list value, 1 item, string item A. So when we run this, that's what we get. The unchanged value remains unchanged. The string value becomes 4 A's. Why? Because it goes ahead. First time it enters this modify state, concatenates 2 A's. Next time, the double A gets concatenated with double A, turning that into a 4A. And same with the number. First time 1 and 1, 2. Next time 2 plus 2, 4. And as far as the list goes, becomes 4 A's in the list. With that, I conclude this video. Please like and subscribe. Please give me any comments or questions you may have. And until the next video, take care. Thanks for watching.